This is the second part of the structure of the nucleus presentation. In this video, we'll focus on the conservation laws in nuclear reactions. Now, I'll put this slide up to talk about alchemy, which is changing one substance to another, one element to another. And scientists have always thought to change lead into gold because they believed gold was the most pure substance. However, there are limitations to doing this. When we've looked at chemical reactions in previous schooling experiences, we've focused on the bonds and the breaking of bonds between elements and atoms and molecules. So for example, at the bottom left of this screen, we have element A, element B, element C and D. Now a reaction occurs between them, and on the other side we still have those elements, but now they have different bonds. Comparing this to nuclear reactions, we can actually create new elements. Now, by creating new elements, we're changing the structure of the nuclei by interacting it with other nuclei or other nucleons. So we've got our diagram here where we've got a neutron interacting with the uranium nucleus. What happens here in this particular example, a nuclear reaction occurs, it becomes unstable, and it splits off into two other elements. When we talk about nuclear reactions, those involving the nucleus and the change in structure, we talk about the conservation laws, of which there are 4 that we will discuss in the following slides. So they include the conservation of charge, nucleon number, mass energy, and momentum. The first law is the conservation of charge, which means that the number of protons in the reaction remains constant. There's no new protons added, none taken away. So when we write our nuclear reaction, as we have here, the protons on the left is equal to the protons on the right. In this case, 9 on both sides. Our second law is the conservation of mass energy. So we might have remembered in previous physics lessons conservation of mass, separate one, conservation of energy, but it is actually the conservation of mass energy when we talk about nuclear reactions. So this means that the number of nucleons remains the same. There's no additional nucleons, no nucleons taken away. So here in our equation we've got 18 on the left, or as our reactants, and our products we still have 18. Now, we did mention in the previous video of when nucleons form or they break apart, there's a change in mass, and this relates to energy. But the conservation of mass energy law still holds that the energy in the system always remains the same, whether it's converted to mass or not. So the nuclear reaction total energy consists of the heat of the reaction, kinetic energy of the particles, and the conversion of mass to energy. So specifically to a nuclear reaction, when energy is taken in and mass is gained, it's called an endothermic reaction. Now remember, this occurs when we have a nucleus that is split into its components, and the mass of its components is greater than the mass of the nucleus. Now alternatively, when energy is given out and mass is lost, this is an exothermic reaction. So this is when we have a number of components and they form to make a nucleus. So the fourth law when talking about nuclear reactions is the conservation of momentum. So this is when the final momentum is equal to the initial momentum of the system. Now let's take an example of uranium-238, which is initially stationary, meaning the initial momentum is 0. Now if it spontaneously decays, we have a helium and a thorium nucleus that travel in opposite directions. Now their total momentum has to equal 0. What this means is that the directions have to be exactly opposite, and the magnitudes have to align in a vector form so that the total momentum is 0. So this means momentum is conserved. So looking at this scenario in a mathematical detail, we can see that because the momentum of the thorium and the momentum of the helium have to be equal, we get the equations in this line here, and rearranging we can find that the helium being so much lighter, it actually travels at a far greater velocity, in the order of 60 times faster. Now if we remember our kinetic energy formula, K equals half mv squared, Now the V, being velocity, plays an important part, and as the velocity of the helium is a lot greater, the kinetic energy of the helium is a lot greater than the thorium.